Hmm.
If you were to look at an image, and as you on a computer screen, and as you blow up the image, you start seeing the graininess. You see the pixels
The pixels, yeah.
of that image, depending on the resolution of it,
Mm.
and that has certain characteristics. Well, the characteristics of this noise are similar to that, which has prompted one physicist, Craig Hogan, who's the director of Fermilab in Illinois, to speculate, and he actually believes that what has happened is that this gravitational wave detector has reached the limit of space-time resolution, and that what it's seeing is sort of the graininess of space. Now, for your audience who's familiar with quantum mechanics and the Planck length, that's really very, very small. So
Yes. Yes.
the Planck effects get down to, say, 10 to the minus 35th meters, 10 to the minus 43rd seconds. I mean, they're at levels that we can't directly detect by any kind of instrumentation. They're so small. They're known only from theoretical basis and ways of inferring them from wavelengths of light and things like that.
Mm.
But this is actually being detected, and it's more in the realm of, say, 10 to the minus 16 meters. So it's 18 or 20 orders of magnitude different from what physicists have previously thought was sort of the limits of the granularity of space.
Mm-hmm.
So that's a curious thing, if this is true, that it is, due to the granularity of space. But what that says is that there's another theory that was put forth by Leonard Susskind and Gerard de Hooft of Holland, that our reality, our three-dimensional reality, may actually be a projection of processes that are sort of encoded on a two-dimensional surface of, say, the boundary of our universe. And this is kind of an odd concept, but it's very similar to the idea of a hologram.
Mm-hmm.
In a hologram, you create a 3D image on a two-dimensional surface.
Yes.
So you're able to turn that surface on its side, and you can, sort of see around the image. You're very familiar with that, I'm sure.
Yes.
One of the interesting things about a hologram is that if you cut it in half, you still have the entire image in each half of the hologram. It's just that the resolution now and sort of the graininess of that image has increased. The resolution has decreased. The graininess has increased by a factor of 2 if you cut it in half. And you can keep doing this and cutting the hologram into other pieces, and the smaller it gets, the image is still there. It just gets grainier and grainier. So what these two physicists are saying is that our reality might be a projection, like a hologram, of a two-dimensional reality. And Mr. Hogan, Dr. Hogan, the director of Fermilab, has actually calculated that if this is true, the graininess that we might perceive in our three-dimensional world is actually higher than the Planck length. So it might be on the order of magnitude of what they're seeing at this gravitational wave detector. I hope I explained that well.
Yes.
But
yes.
Basically, the idea is that we could be living in a big hologram, and this noise on this gravitational wave detector is just at the right kind of level and characteristic that might prove this theory.
Because really, if we think about it in the context of a video game, there as well you have resolution, although we have a simulation of a 3D environment, but we have it in the width and length of the screen resolution that we have, obviously. But much in the same way, reality also actually should have a resolution, and I guess the debate here then is on what the length is, or the how high the resolution is, basically. But what you're saying here is that they've reached the limits already, and they're surprised that it isn't more, how should you call it, more fine than this, right? More detailed than this.
Exactly.
Yeah.
Yeah, because the interesting thing is, and what people don't realize is that physicists really tell us that our space is not a continuous thing. I mean, we think of it as perfectly continuous. You look at the objects in your room, and you can always see something in between 2 points in time. your retina,
Yes.
that creates a limit to the resolution that your eye can have. When you get to that point, you can enhance the ability to see things at finer and finer scales through microscopes and electron microscopes and so forth. But as deep as we probe into the world of the invisible or smaller and smaller scales, everything still looks perfectly smooth and perfectly analog, if you will. But physicists tell us that when you get down to 10 to the minus 35th meters, space is quantized.
Yes.
So you can't even talk about anything that's in between 2 points in space. It's either here or it's there. It can't be in between.
Right.
And they also say that time is quantized by the same way, and the relationship between the space and the time quantization is the speed of light. So the time it takes for light to travel from one Planck length to another is the Planck distance, or the Planck time. So we think of time as moving along smoothly, and science has always used sort of a metaphor of a river. Time flows like a river, but it's not smooth like that when you really get down to these scales. Time chunks along like a CPU on a computer. It moves along at 10 to the minus 43rd seconds.
Right.
And in fact, what the logical conclusion of this model is that the universe is basically states of matter locked into this grid of space at the Planck length, clocking along at a frequency that is 1 over the Planck time, and changing the state at each time, in that frequency. So it's the logical conclusion is that our reality works just like a computer. Basically it changes states every jiffy, every 10 to the minus 43rd seconds, which is unbelievably small. But a good analog to that is just knowing how computer clocking works. It's the same way on a computer program.
Right. But I guess the main thing here though is that we perceive this as being smooth or linear. We don't see the skips or the jumps in between here, so to speak. And it's all about also our perception of it, because we really have nothing else to compare with, right? If we let's say that we are in a computer program right now and never been outside it, we don't know much in the same way when they're living in the matrix. They're born into the system, so they cannot perceive themselves how it is outside that. Do you follow me?
Absolutely, yeah. No, and that's a really good point. I mean, think of people sitting, who have never experienced a movie before, and they sit in front of a movie screen. Movies traditionally were clocked at only 24 frames per second, but your eyes and your brain kind of assimilate that and fill in the gaps between these time frames. So,
yes.
In other words, for us to perceive very smooth motion really only requires about 60 frames a second. It would look very choppy at 24 frames a second, so old movie projectors would flash the light on each frame 2 times, so that you would see each frame twice, and so there'd be 48 frames per second, and that was enough to get past that threshold of motion that our perception has. So we perceive motion with a very, very coarse granularity. So imagine how hard it is to perceive the granularity of space or the granularity of time. The only way we can do it is to think about it and to try to develop experiments that can probe that. And our experiments have gotten to the point where, we're probing things that are sort of 10 to the minus 16th meters, the size of the nucleus of the atom.
Yes.
But that's still very, very far from the theoretical graininess of reality.
Indeed. Okay, so that's really interesting. So that's just one of these recent examples of what we're discovering. We're coming to the end, or the limits of space and space time, basically. Now, do you think, could it be possible though that this is just some kind of faulty machine part that is not measuring things correctly? I'm thinking also of course the Large Hadron Collider in CERN. They have similar problems there, that they've started it up but have to replace parts, and they're not, I think, starting that up again until sometime during the summer this year, I think.
Yeah, I think, to be honest, I kind of feel like they're going to find something. But then you have to ask the question, why did they discover something? There have been a lot of cases in scientific labs where one lab will perform the exact same experiment as another lab and get different results.
Yep.
And there has been quite a bit of research on this effect that lends to the idea that as clean as the experiment might be, the results of the experiment have something to do with the mentality of the experimenters.
Absolutely.
Whether they believe they're going to find something or don't believe they're going to find something seems to impact what they find.
Yes. And that could be said in the context of all the experiments we do. I'm thinking of experiments that is involving in cold fusion. We have allegedly 2 guys that managed to pull it off many years ago, but since then many of the skeptical parts of the scientific community haven't been able to pull it off. That's just one example. We don't have to dwell on that, but I see what you mean, definitely.
Yeah, absolutely. And I think that's probably the best and most recent example. I think there have been, I read at one point, over 80 confirmations of Fleischmann and Pond's cold fusion experiment.
Yes.
And yet there are some that don't confirm it. Another was back in 1980. Wolfgang Pauli had predicted the neutrino a long time ago, and it was discovered. Then there was another sort of anomaly relating to neutrinos about whether or not they had mass. So it was predicted that they had mass. In 1980, the Soviet Union did some experiments that indicated that a neutrino did actually have mass, but other physicists around the world couldn't reproduce those experiments, so they were to some extent discounted. But it does then go to the idea of intent and how this is all another idea tied up in quantum mechanics, that the observer effect, observing things, actually impacts those things.
Yes.
So there's another experiment that's been done not too long ago. I found very interesting in Vienna. You're probably familiar with that one as well. Just last year, a team of physicists basically proved that reality doesn't exist until you observe it.
Yes.
And this came from a long history of the debate of some of the paradoxes of quantum mechanics. So there are a couple things that were very odd about quantum mechanical theory. One is that particles get entangled. So if 2 particles sort of interact with each other at one point in time, then forever it seems their behavior is in sync. So you could take, say, 2 particles that were part of an experiment, a physical experiment that interacted with each other, separate those particles by theoretically light years, and when one of them flips or changes its spin or whatever, then the other one does as well. And it's almost like they're in lockstep, and they violate, theoretically, if one believes that the reason that one particle is changing due to another particle is because they're communicating with each other, or there's some force field between them, then that force field would have to be faster than the speed of light, which relativity forbids. So this is one of the other kind of conundrums of quantum mechanics, is called locality, that there seems to be a violation of locality. In addition to that, there seems to be a violation of reality, in that certain experiments, the results of the experiments depend on whether or not they're being observed. So there's been a long history of sort of a theoretical treatment of this. David Bohm